Okay, great. So I think we could get started. So I think, yeah, most of the people probably are now back. Welcome back, everyone, after the break. I hope you've enjoyed all the discussions in the morning. We are now ready to continue with a very exciting session. I'm really looking forward to this because I also want to learn myself along the way. And I will, Petar needs no introduction. I will let him take over and give us all the details about this session.
All right. Thank you very much, Viorica, and thank you all for following along so far in this program we put together for you all. I do hope you've enjoyed it. I certainly have. And yes, so my name is Petar Velickovic, as mentioned before. I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today I'm going to be doing something a little bit different to what I do usually. I'll be talking to you about how you can build your own graph neural network powered drug screening predictor in a bit less than 1 hour. So what does this mean? I'm going to present a few slides just to put you in the right mood for it, and then we're going to dive right into the coding. So in this not talk, live coding session, we'll be talking about neural networks for graph structured data, or graph neural networks, GNNs for short, as we often call them. You've already heard a lot about GNNs in the previous talks, so I don't think I need to give a lot more introduction on why they're important. You've already heard from many different spheres of application where they could be applied, including from Anari, who are our partners at this event. But you might be asking yourself, why am I not talking to you about GNNs? Why am I coding them? Well, first of all, as you probably are aware of by now, GNNs are a very exciting field, and it's a field I do my research in. And as a result, I tend to talk about them a lot. Okay, and a lot of the talks I've given, both from the point of view of what they are, where are they used, why you might want to use them, I've talked about all of these things so many times, and the talks are all available on YouTube, including in previous EML sessions. I think 2 times at EML now I've talked about these things. So basically, if you want to learn in an abstractified talk way what GNNs are from me, you already have that online, and all these talks are available on YouTube. So if you want to brush up on the abstract stuff behind what we're going to do today, there's a lot of resources for you, and I will share them in the tutorials channel after this talk. So there's both talks and slides publicly released, so many of them. There's a lot of resources if you want to learn this. And, you know, I feel like the Serbian Machine Learning Workshop is a truly special event that is close to my heart, given that I come from Belgrade. And therefore, I really wanted to do something special for you all today. And I recognize that talks are great if you want to get better at mastering some abstract concepts or how to sort information in your head as you sift through tons of literature, but talks will usually not teach you how to translate those concepts to code. They will not tell you what are the underlying primitives that allow the math equations to be implemented efficiently, and they will not teach you what should go on in your mind as you use these concepts to attack a new problem. Typically, talks will not teach you this. And what I want to do in my live coding session is to actually tackle all 3 of these head on. I'm basically going to give you a 1-hour exclusive access to my mind as I try to attack a problem in graph representation learning from scratch. Okay, like you're going to listen to me think out loud and solve problems one at a time as they arise, deal with any compilation issues that happen along the way, basically teach you about what's the way in which a graph representation learning researcher thinks, not how to categorize all that information after I've studied it for 2 years, right? And there's a hidden bonus in it for me as well. When you do a lot of talks and abstractify the information, you tend to become very complacent with your coding skills. And I am strongly in favor of never becoming blunt on your coding skills. So having a session like this, which is going to be a lot of pressure, is going to help keep me sharp for the years to come. And okay, so hopefully this makes sense to you all as well, why we want to do it in this way. And now how it will actually look like. So we'll be together in a completely blank Colab that will fill from start to finish. You can decide. If you feel like it, you can code together with me, or you can just watch the video and follow along, and the session plus whatever Colab we end up with in the end will be released. But in either case, because everything is going to be very linear, we're going to be coding one thing and then it will be a dependency for the next thing. There will be many points where if something doesn't click, it's going to get worse and worse as we go along. So if something doesn't make sense and you want it resolved, raise your hand frequently, and I trust Viorica will be keeping an eye on these questions so she can forward them whenever we open a new code block to hopefully try to resolve these issues as they arise. Okay. There are no big prerequisites. I expect if you're following along with me that you're reasonably familiar with Python and that you've used NumPy before. That's all. We will be using a deep learning framework called JAX, and I'll be using pure JAX, not libraries on top of JAX, because it's basically NumPy with the capability of gradients to allow you to train a machine learning model. And I picked this rather than going with the established graph neural network library, simply because it will allow me to very clearly show you the primitives, like what are the underlying matrix operations I'm thinking about when I'm actually writing a GNN layer. If you actually want to take some of the concepts I've taught you today and build a production-worthy system, I wouldn't recommend using pure JAX. I would recommend using a dedicated library such as Giraffe or PyTorch Geometric. Okay. So hopefully that makes it clear what we're going to do and how we're going to do it. And just to set a bit of a context, so I grew up in the late 1990s, early noughties in Yugoslavia. And around that time on the TV, there were a lot of adverts about HIV. So there were a lot of adverts that I think I remember one markedly because it kept being looped back over and over again on all the TV channels. Budi pametan da ne budeš pozitivan, be smart so you don't become positive. So basically, it seemed to me like there was a big panic around this thing, to me as a 7-8-year-old person with a mind of an aspiring scientist. Like to me, it felt like if we're able to treat HIV, that basically means you beat the game, like you solved the most complicated challenge humanity has right now. So, you know, it's a bit of a cliche, but the things that you hear about a lot as a kid tend to stick with you as like these grand challenges that would be really fantastic if we solve them. So could we try to teach a machine learning system to find good treatments for HIV? Maybe. Let's see if we can put our graph representation learning knowledge to the test. What we're going to do in this session is we're going to train a graph neural network over a data set for drugs where we know how the HIV virus responds to them, like whether the drug is effective against HIV or not. So it's a binary classification problem. And then once we've taught a model like this, we will deploy it on a test data set, which is hidden from us at training time, to see how powerful the model is. All of this in the space of 1 hour from scratch, no GPU. So no pressure at all. Let's see what we managed to do. So it is now time to go to the Colab. Can you just confirm that you can still see my screen?
Yes, I'm seeing the slides.
And now you should see the Colab.
Now the Colab, yes.
Awesome. So GNN-based screening predictor, question mark, exclamation mark. Let's see. And I heard feedback from previous sessions that we should zoom in the text a little bit. So I hope this should be enough, but if we need to zoom in a bit more, please do let me know.
Sorry, okay. For people who joined, there's the link for Colab in the tutorials channel, in case anyone missed it.
Yeah,
please go there in the tutorials.
Exactly. In case you haven't used Colab before, I put a link in the tutorials channel that should allow you to very quickly get up to speed with it. Okay. So we now have in front of ourselves a blank screen that allows us to type Python commands, and hopefully interesting things will come out. All right. So first, what I'm going to do is I'm going to install a few libraries that I know Colab doesn't have, and they will be very necessary. So the first command I'm going to install are OGB, and the other one is Optax. So the first package, the OGB or Open Graph Benchmark, is a wonderful collection of graph learning data sets. So it's a fantastic resource if we want to access publicly available data, such as the data on HIV inhibition that I just mentioned. And Optax is a library that allows us to easily access the state-of-the-art gradient descent functions inside JAX. So JAX will get us almost all the way there. It will compute gradients for us, but then you still need a way to decide from those gradients how to update your neural network, and Optax will help us with that. I believe all other libraries that we need will be already installed inside Colab. So without further ado, I'm just going to hit run. And it might take some time until we connect to a CPU backend, and it will take a bit more time for OGB and Optax to get installed. And I'll let you know when that finishes. Yep, 12 seconds, all good. So we are off to a good start. Now we are going to try to understand a little bit more about the problem that we are solving. So we're going to look into this OGB library and see what kinds of graphs can we extract from it, maybe inspect them a little bit, understand a bit better how our data looks like and what it is. So to do that, I am first going to load a library from OGB. So OGB graph prop pred, which means graph property prediction. Specifically, we represent molecules, the molecular representation of drugs as graphs, and we want to predict a graph level property, like is this entire graph an inhibitor of HIV or not? Graph prop pred dataset. So this graph prop pred dataset, and you can go on OGB's website to get a detailed instructions on how to build code like this, is going to be a general wrapper that allows you to load data sets of all the graph property prediction tasks that OGB has. So now that we have that, we can build our own data set by loading it. So graph prop pred data set. And the way in which you tell it which data set to load is by telling it what the name is. So specifically, we want OGB graph task molecular HIV. So this data set will load a bunch of molecular compounds for us and with their associated flags, whether or not those molecules are potential HIV treatments or not. And just so that we can play around inside this data set, I'm going to pull out one particular example out of it. Like it's a very easy data set to use. It's just a list. So I can take data set of 0 to get data point number 0. And each point has a graph, which is the molecule, and the label, which is a 0, 1 flag, telling you whether or not this molecule is a HIV inhibitor. And let's just print some interesting stuff from these guys. So graph will be, if I recall, a dictionary. Therefore, we can look at the keys to see what kind of data is given to us inside a graph. And we can print what the label looks like just to be confident about that. So keys are, label is. All right, so let's try to spin this. It will take some time. It needs to download the data set and actually unpack it for us and pre-process it. So do all that nice conversion from raw molecular representation into a graph. So we don't have to worry about that stuff and just dive right into the machine learning. And yeah, it's done. It shouldn't take too long. It has only about 40,000 molecules and they're not very big. So this is fast, even if your internet isn't that large, isn't that fast. And here we can see what are the different data that we get for every particular graph inside our data set. So a label, as we discussed, is a simple binary label, right? 0 if it doesn't inhibit HIV, 1 if it does inhibit HIV. And here we have the different pieces of data that we can collect from this data set. So specifically, there's some potentially clear stuff, like this molecule has a certain number of atoms, and that would be the number of nodes parameter. Then there's features inside the nodes, features inside the edges, edge index. These might not seem very clear. We will explore them in the next cell. So for now, we're not training any machine learning models. We're just trying to understand our data a little bit better if we haven't seen this data before. So are there any questions at this point, or is it so far so clear?
Yeah, I think this looks good so far. But yeah, please raise your hand if there's a problem. At least 2 people gave a thumbs up that they're coding live with you. So
yay, perfect.
Exciting.
Perfect. All right, so this is okay. So now we've loaded one graph and now we can play with it. So before we try to do anything with the data set, like keep the data set in mind. We'll come back to it, of course. But the graph seems to have a lot of interesting data inside it. So let's see what we can do about that. So maybe let's just print some interesting statistics about this graph. So obviously, like I expect the graph of number of nodes to be an integer, but I'm not sure. Let's see if that will give us an integer telling you how many nodes there are. Node features, I would expect to be some matrix of the shape number of nodes times number of features, right? That basically should make sense. Like it gives you a matrix where every row gives you the features of every atom inside this graph. And then there's also the edge features. And this, I'm not completely sure what it's going to look like, because there are many different ways to represent edges in a graph, and we will discuss actually a few of those ways during this live coding session. So I'm just going to look at the shape for now to get a feel for what it might be. And the edge index, I am only vaguely aware of what that might be. So I'm quite curious, as a first approximation, to see what this might look like as a shape. So let's see. Okay, these numbers should already help us quite a bit, right? So indeed, my hunch was correct. We have 19 nodes in this particular graph, so 19 atoms in the molecule, okay? And the node features, indeed, it seems to be a matrix where the number of rows is equal to the number of atoms. That's great. And there seem to be 9 features inside every single one of these atoms, so that's nice. We can discuss more about what some of these features might be in a second, but for now, we have a 9-dimensional vector in every single one of the atoms in our graph. Edges, well, before I might have had doubts what these two guys might be, but now when I see this match of the number 40, such a static number tells me, okay, this graph probably has 40 bonds, so 40 chemical bonds between the atoms. And the features here tell me for every one of those 40 bonds, I have 3 features attached to them. That could be, for example, is it a single bond or a double bond? Is it in a ring or something like this? And then that also directly tells me what this array of size 240 means, because obviously there's 19 nodes and 40 edges. You need to have some way of relating those edges to the nodes, right? Because every edge connects 2 nodes. So this edge index basically tells you that. For every single one of the 40 bonds, it tells you what are the 2 atoms that, that are connected by that particular bond, okay? So does this make sense before we move forward?
I think so. We have now 9 people coding live.
Wonderful, wonderful. I am highly in support of joining me along for this journey. So, right, let's maybe try to visualize what these features look like, just to get a feel for it. In machine learning, we often have to deal with features that have weird scales and stuff like that. We might have to normalize something. So let's just get a feel for what this thing looks like. And so just to make it smaller, I will take the first 5 atoms and look at all the features that they have. And I'll take the first 5 edges and take the top 5 and take all the features that they have. Do I have any bug in here? Well, I think not. So yeah, this should give you a feel for how node and edge features look like. So it seems like all of my features are integers, and some possibilities for what these integers might be. In the case of the nodes, which are the atoms, I might want to encode what atom is this? Like, is it a carbon? Is it a nitrogen? Is it oxygen? All these kinds of things. What's the total atomic weight of this molecule? Basically, what's its order in the periodic table? What's its charge and stuff like that? What's its valence? There are all of interesting properties from basic chemistry that you can attach as various features. I don't know exactly which ones are in this particular data set, but they chose 9 of them to represent each atom. And I assume this first feature, which goes up to like 28, could be the atomic weight. And keep this in mind. So we have a feature that's quite big. We might have to, think a little bit about normalizing this at some point in order to not have blow up in our neural networks. Okay. And edge features seem to be a bit better behaved. They're just 3 integers, and I assume it's like single, double, triple bond, or is it in a ring or something like that? Okay. So hopefully this gives you a bit more feeling for what our features look like.
Sorry, Petar, sorry for interrupting. Could you just very briefly re-explain the different variables? So the nodes, the edges, and the features. Someone is asking to please repeat this.
Yeah, of course. So we are dealing with a graph, which is a molecule. So it's composed of nodes, which are different atoms. And those atoms are connected together by chemical bonds, which we call edges. Okay, and this is just a representation of them. So our node feature matrix is of shape 19 by 9, which means that for every one of our 19 atoms, we have a vector of 9 features telling you, describing that particular atom and where it is in the molecule. Okay, so is it carbon? Is it nitrogen? What's its atomic weight? What's its charge? And so on and so forth. And for every single one of the bonds, you have 3 features which presumably tell you, is it a single, double, triple bond? Is it in a ring? Or these kinds of properties from standard chemistry, basically. So nothing too special, I would say. I hope that answers the question. Okay, so now that we have explored this data set, we should think a little bit about what is the best way to feed that data into a machine learning model. And this is where graphs get a little bit funny, because there are many ways in which you can feed the graph structure, which is like a sparse structure of connected nodes. And as you know, GPUs and TPUs especially tend to prefer fixed shapes for doing their computations. Otherwise, you run into a lot of problems. So one thing we can do, and what I'm going to do here, is the simplest possible solution of not feeding in this sparse edge structure of just a list of pairs of nodes, and then we have to worry about indexing and these kinds of things. But I'm actually going to build something a bit more mathematically commonly used, which is the adjacency matrix. So I'll build something of shape 19 times 19, which will tell me which pairs of nodes are connected together. And I'm actually going to feed that whole matrix rather than this list of edges here. The reason why I'm going to do that is because my molecules are small, so I can get away with the n² complexity. And it will be a lot easier for us to think about what graph neural networks are doing, at least at the beginning, using matrix operations. So that's the reason why I'm going to be doing this. So now, basically, I'm asking you to convert me this list of edges, this 240 thing, into something that might feel like a 19 by 19 adjacency matrix. It's maybe a standard exercise you might get in a coding interview. So let's see who can get a job at Google. I hope I can get a job at Google. Let's see. So first, just to make sure that my intuition is right, I'm going to take the edge index and print out what it looks like. So indeed, as I expected, it's 2 arrays with integers, and the corresponding positions tell me which nodes are linked. So 0 to 1, 1 to 0, 1 to 2, 2 to 1, and so on and so forth. Okay, so we're now going to be dealing with matrices. So I'm going to need to import NumPy. NumPy is the standard library you'd import in Python to deal with matrix operations. And I'm going to be talking about now, I want to convert my edge index to a matrix. And because the edge index in and of itself doesn't tell me how many nodes there are, I'm just, for convenience, going to pass how many nodes there are as an extra input. Okay. Okay, so we're going to start our adjacency matrix. And for reasons that will become clear later, it is usually a good idea to keep a node connected to itself. Because a GNN will basically be passing information along the edges of the graph, as long as you have a self connection, it makes sure that the node is always aware of itself. So that's why I'm not starting with NumPy zeros, but I'm starting with NumPy I, which is the identity matrix. Okay, and now I just need to do a for loop. There are probably way more efficient ways to do this, by the way, but I'm trying to come up with these things on the spot rather than think of the most optimized way to do it. I'm going to do a for loop through all of the edges inside my edge index and the adjacency matrix inside the edge index at position 0 and edge index at position 1 should be set to 1. There exists an edge there. Right? And maybe just to get a feel for whether we've done it correctly. Graph, num nodes. Right? So for our previous graph that we talked about, we will take its edge index and we'll take its number of nodes. And we'll try to see, do we get a proper 19 by 19 matrix as a result of doing this? And indeed, this looks roughly correct, right? So the main diagonal is all ones, as I said. and say you have connection between 0 and 1, it is there, connection between 0 and 1. 1 and 0, also there. And then, you can go through it like this, and you can see that all the coordinates that were in the original array match up where they're supposed to be. And also conveniently, because this molecule is symmetrically connected, whenever there's a connection from I to J, there's also a connection from J to I. Okay, so I hope this makes sense. We now have a 19 by 19 representation of the edges in our graph, which we can conveniently use as input to a machine learning model. Was there any question at this point?
Yes, we have 2 questions. So maybe I'll go with the one from the chat here first. How does having the self connection compare to having skip connections?
Very good question. For some models, they are equivalent. For some models, it is better to have the skip connection. But this is obviously going deeper than I have time to investigate. I highly encourage all of you, by the way, to play with this code after we're done with it and just try all those variations for yourself. But that's a great question.
Okay, one more question, just to say there are 19 people now coding. Yes. So a question from Senad, how careful do we need to be when normalizing the data? Since our features can contain something like positioning, a periodic table, is it advisable to normalize such features? And if not, how would we handle having different features on such different scales?
I don't know. We're going to find out. I'm going to normalize on the spot if we need to. So, but that's a great forward thinking. I like that. So I hope we all agree that this adjacency matrix now makes sense. I'm going to cut it out just so we can see the code more clearly. And okay, I think now we have all we need to start implementing our first graph neural network layer, right? We're going to be using our node features as the input, as the collection of the features in the nodes, and we're going to use our adjacency matrix. For now, I'm going to ignore the edge features because including the edge features makes things a little bit more complicated. Like I want to start with a very simple model, but then as we go along, we will include the edges at the end, hopefully, if there's time at the end. Okay, I believe we have about half an hour left from this point, so hopefully there's a chance we'll be able to do that. Okay, so I said we will be using JAX as our library for machine learning with matrices, and specifically JAX has this very fantastic thing called JAX NumPy, which I always import as JMP, and basically it is just like NumPy, exactly the same signatures as NumPy, but it will allow you to take gradients of all the things that you do. So you can express your neural network, your graph neural network, purely using JAX NumPy operations, and then we can update our parameters using gradient descent. So that's the reason why I went for JAX, because it allows us to basically just use our existing knowledge of NumPy and get everything done based on that. So I'm going to include some premature optimization because, as we know, premature optimization is a good idea. I'm going to do just-in-time compilation of this neural network function that I'm going to do. So don't worry about this annotation too much. It's there just to make the code more efficient. So I'm going to write my first simple GNN layer. And what does this layer need to have? Well, because it's a learnable layer, it needs to have some weights, so some parameters that we're training. And the inputs to our GNN layer are node features and adjacency matrix. So that's the main inputs to our model. Okay. The first step we're going to do, like every deep learning system, always starts with a linear transformation. So we're going to take our node features and transform them using the weights. And as you probably know from basic MLP setups in machine learning, the way you get that is by doing a matrix multiplication of your features and your weights. So we're going to perform a NumPy, JAX NumPy matrix multiplication of our features with our weights. So as long as weights are of the shape previous features times new features, this will take our features to a new feature space, right? So if I had something of shape n times h, and I multiply it with h times h prime, as a result, I'll get a new set of node features, which now have n and h prime in each node, right? Now I need to somehow use the graph structure, right? So I have features in every node, but I want to somehow use my adjacency information to combine the nodes together. And what's the simplest thing we can do? Well, basically every node can take the sum of all of its neighbors as its own feature, right? It's a way to kind of regularize it around the local neighborhood. Well, if I'm summing across all of the neighborhood that I have, then that's, if you think about it a little bit, that's equivalent to multiplying with the adjacency matrix. So making our first GNN layer, it's as simple as writing matmul of adjacency matrix with the latent. So to give you a feel, we had something of shape n times n, which is our adjacency, and n times h prime. It gives us an updated thing of n times h prime, but now with all the neighbors incorporated in every single one of those nodes. And this is the reason why I said I'd prefer to write this in JAX rather than take a graph neural network library. It allows me to very explicitly tell you about the matrix algebra behind all of these things. And lastly, you cannot have deep learning without an activation function, and JAX conveniently gives you activation functions. So I can apply a ReLU to every single one of my outputs. Standard thing. You can use any other function that you care about, like hyperbolic tangent or sigmoid or whatever. And yeah, that is pretty much it, right? So we have just implemented a single GNN layer. Are there any questions at this point before we start to make a network of these guys?
Not so far, but please do post in Slack or here if you have any comment or question.
Okay, so assuming that this is fine so far, I'm going to now take one of these layers and stack more layers into a network. And this network will have the collection of all parameters. The way I'm going to do it is I'm going to have a list of weights, where the ith element of params will give me the weights of the ith layer, just to make it easy to work with. And once again, you give it features and adjacency matrix to start with. Okay, so let's start stacking more layers. Our latent features are initially just the input features. So this is like at input step 0. And now we go through all the layers inside our parameters. -1. The last layer is special. I will explain why the last layer is special in a second, but all the layers before the last one are of the same form. They're as simple as you just apply your simple GNN layer that we just did to the params of that particular layer. Features, sorry, not features, latent. That's the part that gets updated at every step. And the adjacency matrix typically stays the same, although there are interesting methods nowadays that try to modify the adjacency matrix too. Okay, so this should be your usual run-of-the-mill stack more layers. Start with the input features and stack, 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 right? And now, if you remember, we are classifying the entire molecule for something, right? This layer here will give you features in every single node, but we want an output on the level of the whole graph. So we need some way to compress the features of the whole of the individual nodes into features of the entire graph. There's a lot of theory behind how to do this, but basically it boils down to I need some function that I can apply to my nodes that will be independent of the order of the nodes. So anything that's permutation invariant, as we say, is going to work well to derive our graph level features. And one very simple thing you can take is just the average. So take our latents, and if you remember, our latent has shape n times h, right? How do we go from that to just h? Well, we need to take the mean over the axis 0, and that's going to give us something of just shape h. Yeah. So now we've reduced our collection of node features to something that's just the features of the whole graph. And this works, by the way, not just for means. You can take max, you can take sum, all of those operations work. And it's a good exercise to check which of them works best, by the way. It's very dependent on the problem very often. But this is generally how we go about doing it. Okay. And finally, once we have those graph level features, we can apply our last layer, which gives us a single binary classification output. This is your standard logistic regression layer that you see in a typical machine learning course. So you take your graph features and you multiply it with the parameters of the last layer. And this matrix will always be of the shape h times 1. So as a result, we'll have just one output. And that will be our logit. That's it. This is our prediction, our value that says how likely it is that this drug inhibits HIV. The higher the value, the more confident the model is that it is indeed an inhibitor of HIV. So does this make sense? And the code compiles, yay.
Just a quick question from Bilal, if you could please kindly explain again the second line in the simple GNN layer, so where you multiply with the adjacency matrix.
Yes, so I want to make the features of every node be a function of all the nodes in the neighborhood, like the immediate node it's connected to. One simple way to do that is to just take the sum of all the neighbors. And to take the sum of all the neighbors, it's equivalent. You can convince yourself it's equivalent to multiplying with the adjacency matrix because it has ones exactly in the pairs where there are connections. Everywhere else it's 0. Yeah. Does that help? Okay, perfect. So we are almost ready to train our model, almost ready. We need to, as you know, in machine learning, we need to also define a loss function. And for those of you who have done binary classification before, you will know what we need is a binary cross entropy. Right? And I'm going to do some standard numerical hacks that cause this binary cross entropy to behave well. So this is maybe the only part that I'm kind of taking out of my brain, and I'm not really explaining it that much, but it's basically just the implementation of a standard binary cross entropy function. So this part of code has nothing to do with graph neural networks. Like, you can look it up somewhere if you want to learn more about how to do binary classification, but this is basically a more numerically stable way. Like, you always do this trick of subtracting the maximum value from your logits, and then there's this kind of way to go from raw unnormalized logits all the way to the cross entropy loss without ever computing the sigmoid function, which is numerically less convenient. And basically, it's some clever combination of logarithms and exponents. I hope I get this right the first time. All right, plus GMPX minus logits minus max val. So unfortunately, as I said, like, I am not particularly able to give you a nice explanation of this formula, but it's basically a bunch of algebraic manipulations starting from the basic cross entropy formula to get something that's numerically stable. And you can look up a formula like this, will appear all the time in texts on binary classification. And then we just take the mean value of the loss across all the different logits and labels. So here, logits are the prediction of our network, and labels are the ground truth. Like, is the ground truth 0 or 1? And this computes the loss function that we then optimize using gradient descent to train our model. Okay. I am probably unable to answer any deeper questions about this function on the spot, but I trust that the people who are coding together with me can hopefully transcribe it without a lot of problems. Okay, so now we can define our loss. So a loss function is always defined with respect to parameters, right? Like, we have some current parameters, weights of our model, and we want to define what's the gradient with respect to those parameters of the loss function above. So for a particular input, features, adjacency matrix, we can define logits as the output of our network. So we call the network to get the logits, and then we just return our loss value. Oh yeah, and this means I also need to give labels. So for a full training example, where we have a graph given by features and adjacency and the label 0, 1, I can now define my logits by calling my network, and then by calling my loss function on the logits to get the final loss. This should be standard for most of you who have seen a machine learning tutorial before. And lastly, it might be good to have some way of computing accuracy, like how accurate my model is. So for a particular set of parameters, and for a particular graph and the ground truth label, we can, oh, sorry, I guess we don't need that. We can just take logits directly. So logits and labels. This is a fun formula that allows you to compute accuracy in a more kind of streamlined way. And people often use it in machine learning papers. So this here is like, I check whether my classification threshold is bigger than 0. So positive values roughly mean the network is predicting yes. Negative means the network is predicting no. And the label is either 0 or 1. So whenever the prediction of the logits matches the prediction of the labels, that's a point for us. And then we can compute accuracy by taking the average of all of those predictions. Okay. So are there any questions about this block? These are mostly just standard neural network and evaluation blocks that don't have anything to do with GNNs.
No questions here, but there was a question related a bit to the adjacency matrix. Chinmay was asking, many GNN layers take a weighted average rather than directly the adjacency or the summing, how you did. Is that a strict
I will
rule, or?
I will avoid answering this question because there's something I would like to teach based on this. But yes, that's a very good question. That is a very good question that I hope will be answered very soon.
Great.
So,
Tejas is asking about if you could explain the formula for accuracy again, just very briefly.
Yeah, so logits is a value from minus to plus infinity, saying how confident is the model in the prediction. And we typically assume bigger than 0 to be plus and less than 0 to be minus. And the label is 0, 1, telling you the ground truth. Is it not, or is it? So logits bigger than 0 is it predicting 1? And labels bigger than 0.5 is the ground truth 1. As long as those two values match, it's a plus point for our accuracy. Otherwise, it's a negative point for our accuracy. And then we just take the average of all of those. It's a more concise way of maybe more explicitly writing it out, which is what we tend to use as a trick to write these things more cleanly. But I hope that helps. Okay, so I promise you we are almost ready to train our model. I'm going to now import Optax, which is, as I said, a JAX library that will allow us to actually take gradients of this loss function and update. And because we're careful machine learning researchers, we are going to have a training and a validation test. We're not going to train on everything. So if you remember, our dataset object has a lot of fun functions we can use. And one of them is getIndexSplit, which will tell us what are the training and validation data sets and test data sets for this particular case. So I can take all the train indices and validation indices in the data set as just asking split index to give us train and valid, I believe. Yes, okay. And it's going to be very useful for me to keep track of the input dimension. So that will be, so if you remember, a graph of node features gives me a matrix that is of the shape number of nodes times number of features. So if I take the second element of this shape, it will give me how many input features we have in the nodes. I know it's 9, it's always 9, but it will be more convenient to keep it as a variable. Okay, sounds good. So now we are ready to start training. And we need some hyperparameters in our model, which is how many hidden dimension features are we computing, how many layers we have in our model, how many epochs are we going to train for, and what's the learning rate. So all the standard stuff you need for a deep learning system. And we're going to start with a collection of parameters. We need to initialize them. And basically, the input layer is always the special one, right? So if you remember, we need some random matrix to map our input features to the feature space of hidden dimensions. So we basically need some randomized, like initially we randomly initialize our parameters to begin with. So we take random normal. Specifically, this matrix needs to take the input dimensionality to the hidden dimensionality. So this will transform our node features from the input space of 9 to the hidden space of well, we will decide 128 or 32 or something like that. Another thing, these basic normal value distributions tend to explode quite a bit. So I'm going to use the standard trick Jan-LeCun initialization, divide by the square root of the input dimension. So that will just make these values a bit smaller so that they're easier to work with. Now for all the layers, well, all the middle layers to be precise, it's basically the same kind of matrix. So I take my parameters and I append numpy random randn. Now we just map hidden dimensions to hidden dimensions. And we divide by the square root of the input dimension. This time, sorry, hidden dimension, because that has changed. Okay. So these are all the intermediate layers of our GraphNet, which just keep us from hidden dim back to hidden dim. And now finally, for the last layer, we need to have a prediction from the graph features. So that's hidden dim to just one value, the logit, right? Whether or not it's a candidate drug or not. And once again, I do this division just to keep things easier. Yeah. So this is our collection of weight matrices that we're going to train, and we store them in this list of parameters. And we create now our optimizer. There are many popular optimizers. I personally like to use Adam because it often works really well. So we have some optimizer that takes a learning rate and applies our gradients. Adam has some state associated with it. It keeps track of some statistics. So we need to initialize it in order to keep track of that state. And now we're ready to define what a single step of gradient descent looks like. So single step of gradient descent, we have some existing parameters. We have an existing state of our optimizer function, which applies the gradients. And we have a particular example. So features, adjacency matrix, and labels. So far, so good. We compute loss and gradients by using JAX's convenient function value and grad, which will basically compute our loss function, which we defined here, and return its gradient with respect to the first parameter, which conveniently are all of our parameters. That's exactly what we want. And the specific inputs to the function are params, features, adjacency matrix, labels. Okay. So far, so good. Now that we have that, we can compute our updates and update our state, if I remember correctly, which allows us to take opt update, grads, opt state, params. So this computes how big is the gradient. Well, the grads part computes the gradient with respect to every single element of those matrices. And this opt update actually runs Adam to compute how I should update every single one of them based on those gradients. And now finally, I can update my parameters. So apply the updates, params, updates. Okay, great. And now I can finally return all the things I need to update. So params have been updated, opt state has been updated, and I have a loss. I can just return my loss to keep track of what my loss function is like. All right, now let's write a training loop. Almost there. So we're at epoch 0 initially, and our step is 0 initially. While we still have epochs to go, we go through all the indices in our training data set. We take a graph and a label, which is a data set of IDX. And we take our node features, which is graph of node features, I think, yeah. And we take the number of nodes. All right. And we can compute our adjacency matrix, which requires us to call our function that we previously had, convert edge index to matrix. Graph of, we need the edge index as the first parameter, and we need the number of nodes as the second parameter. Okay. So now we have our node features and our adjacency matrix. So all we need for a training example. So now finally, we can update our parameters, our opt state, and compute the loss at the same time by calling our step function over those things. So params, opt state, node features, adjacency matrix, and label. All right. So this does a single step of training. And if you're like me, I like to periodically keep track of what my loss is like. So I'm going to say at every 1,000 steps, print the step and print, oh, I have a typo in there, all right, and print the loss value. Okay. And obviously never forget to increment step by 1. Okay. This is a very inefficient implementation, by the way. There's no batching, there's no parallelization or any of this kind of stuff. But hopefully it illustrates a very simple training loop, which we should be able to run on a CPU. Okay, I'm getting a bit pressed for time, so let's see if I can manage to finish this on time. Validation predictions empty, validation labels empty. I now need to collect I need to evaluate my model on the validation set. And basically repeat all of this again to extract a validation example. So now we have this for our validation data. And we append the network output with our parameters, our node features, our adjacency matrix. And because it's a list, I take the 0th element just to make it easier. And val labels, I will append the val label. Okay. And now I can finally compute my accuracy. So I compute accuracy of a JMP array of these val preds, JMP array of val labels. And I can print for this particular epoch, I got this accuracy. Okay, it's going to be a wonder if this compiles first try. Epoch plus equals 1. And finally, when we're done training, our parameters might be useful sometime later, so return them. Okay, so what I've done here is I've mainly just, oh, this is wrong. There's a bug here, nice. What I've done here is I've just written a simple training loop. So most of this is not related to graph neural networks, but I needed to write it in order to be able to train my model. And now finally, I can try to train my model. So let's say hidden dimension 32, number of layers 2, epochs equals 1, and learning rate 0.001. Let's see what happens. Does this work? It actually compiles. Oof, crazy. Now let's see whether it actually did something useful. It starts off with some kind of a loss value, which is reasonable, but maybe we won't see such luck going forward. And remember, I'm printing the loss every 1,000 steps, and it's going to take a while for it to compile. Okay, so the loss is going down, so something meaningful is happening. That's great. That's great. Wonderful. Oh, wow. Okay. Okay. So far, so good, I guess. And now it's running on the validation set because there's 32,000 examples in the training set. And there we go. We have a validation accuracy of 97%. That sounds really awesome, right? Well, there is a tiny caveat in here, which is most drugs are not HIV drugs. So there's a lot of class imbalance in this data set. So if you go back and you actually run the ROC score or the F1 score or anything which keeps in mind the class imbalance, you will actually get the more sobering number like 60 or 70. So just to be clear, I wanted to show you that part too, but apparently it doesn't work. And another thing I was expecting to happen in this first run is I was expecting an infinity gradient to happen somewhere in here in the middle of the training. Because of one of the questions that was asked by the participants, do we typically normalize the adjacency matrix? Like a matrix of this form with ones everywhere is going to have high eigenvalues, and multiplying it with the latent here will explode the features, leading to infinity values and NAND gradients. So typically what we might actually do in practice is to divide the adjacency matrix by the sum of the adjacency matrix over minus first axis. And just to make sure broadcasting works properly, I'm going to retain the dimension there. So this is the actual version that I wanted to use. But yeah, I did not get the infinity gradient. So it seems like we have a model that compiles. It's accurate 98% of the time, even though in reality, most of the time it's saying no rather than yes. So you need to plot something more realistic like the ROC curve to actually see how predictively powerful the model is. Okay, so this terminates the coding session. I realize that I'm a little bit over time, but if it's okay with the next speaker, I would just like to take a few minutes to present a few slides at the very end, having successfully reached this milestone. So you just might be asking yourself, could I summarize everything we just did? And is any of this actually any useful, right? I built a toy model on a toy data set of HIV inhibition data based on some drug inputs, right? Well, let's summarize what we did. So molecules are graphs represented by atoms as nodes, bonds and edges, features like atom type, and so on. We train a GNN to predict some interesting task, like whether or not this molecule is a potent drug. And it turns out when you have a pre-trained model like this that is trained on some data set you do know, you can run it on molecules that are any molecule, not just the molecule in your data set. And sometimes it might give a very high confidence that that molecule is a drug that you care about. And in one case where a graph neural network like this was trained on antibiotics, they ran it on this previously unstudied molecule in the context of antibiotics, which is halicin. And they found that even though it looks very weird for an antibiotic, it's a very powerful antibiotic. And especially because of its weird structure, it was used as it had a very potent mechanism of action that beat a lot of the different systems that was powerful against antibiotic resistant bacteria that got used to the kinds of antibiotics we would normally recognize. And this was a big discovery. Around February 2020, it resulted in a Cell publication, was reshared by Nature, Financial Times, BBC, and so on and so forth. So in summary, if we exclude some hyperparameter tuning and a team of chemists, which I could not reasonably find in the space of 1 hour, everything you've seen here, like build a data set of drugs with known properties, train a graph neural network over that data set, deploy then that graph neural network on some data set of unseen molecules, it's in principle sufficient to make a breakthrough in drug discovery. And I'm sure Stan will tell me all the ways in which what I just said is completely wrong in his next talk. And another big point is that unlike this HIV data, which has now been studied to death because it's part of a standard graph benchmark setting, there's a lot of relevant data for rare diseases that's just sitting there waiting to be used. We have way more data than we have people willing to do these kinds of investigations. So beyond that, we can just say graphs are pretty much everywhere. And I would like to thank you very much for your attention. I hope you enjoyed it.
Thanks a lot. Thanks a lot, Peter. This was really, really exciting. And yeah, people are really, really grateful for this very nice and in-depth tutorial. So there were a few questions. So I think we still have 5 minutes until the next talk, so we can probably go over those. So Luciano was asking if we need to add bias coefficients in the network.
Yes, that is one more detail which I have left out just to keep the matrix equation simpler. But in principle, all of those matrix products I computed with weights would be in a more high-level library like Haiku or Giraffe. They would just be linear layers, which would inside them have hidden a bias term. So yes, definitely don't take my coding as an indication that you shouldn't use bias terms. Think of it more as this is how I think as a graph machine learning researcher when I attack a new problem. Yeah.
Okay. Also, you mentioned at some point that you feared that there would be a divergence in the training, and Chinmay, Haitam was asking, but you added a clip. You add a clip in the loss function. Wouldn't that prevent the divergence?
No, that clipping is just actually, it's the way the loss function itself is implemented. So the numerically stable form of cross entropy starts with that kind of clipping operation, just it's part of how it's implemented. So that clipping has nothing to do with stabilization. Yeah.
Okay. Then Chinmay asking, do things work fine without using explicit normalization layers in general?
So here we were lucky. Once again, I wasn't expecting this. I was expecting I would have to normalize the adjacency matrix and I'd have to normalize the features by dividing by the maximum feature value or something like this. Thankfully, we didn't run into those problems because I was about to run out of time. But you know, in general, yes, I would highly recommend normalizing everything, even as a first step. Although it's useful sometimes to see how well you can do even with an unnormalized data set. But in this case, like I'm still surprised we were able to fit this data set without exploding with a feature of size 50 or something like that. So in general, I would have expected normalization is necessary.
Okay, great. So I think these were all the questions that that we received. 27 people in the end did the coding with you. So this is great. And yeah, everybody's sending positive messages in the Slack. So thanks again, Petar, for this great session.
Thank you so much. And I think this is a great way to introduce our final